Okay, so before I start my today's lecture, let me briefly talk about my last few lectures and give you a very small summary of what we have been doing till now. Well, the first lecture of this series is the Hadron classification 1, lecture 1a, where I talked about the eightfold way and also the subsequent basic quark model. I also discussed some problems with you and also discussed very interestingly a wave function problem and what sort of elementary particles cannot exist based on the static quark model. In the next lecture, basically we have not shown here, it was a recap of this lecture 1a but in a much simpler fashion, and afterwards I talked about the quark line diagram, or also known as color flow diagrams, in lecture 1b, followed by detailed discussion on Zweig's rule and various applications. And finally, in the last lecture, which is lecture 2, I talked about baryons and mesons in the UD sector, starting with the isospin algebra and the construction of flavour state functions of baryons in the UD sector. Afterwards, I talked about the spin states of 3-quark system, and finally we talked about and discussed in detail the ground state, how to derive the ground state baryon wave function in the UD sector. I have written down the expressions for the spin flavor state functions for delta spin down, proton spin up, and also the neutron spin down cases. And finally, I talked about the isospin representation of antiquarks and construction of flavor wave functions of mesons in the UD sector. So this is what we have been doing. So what now? Today, in the third lecture, now I am going to expand and I am going to talk about the hadrons in the UDS sector. Okay, so let's start with it. So what do we see here? You see here is the J pi is equal to 0 minus pseudoscalar mesons, and this here, these are the quark constituents of them, and also the J pi half plus baryon octet, the various quark constituents. Now in the lecture 2, you will find that I have talked about the UD sector only. That means only those mesons and baryons I have tried to discuss their flavor spin state functions which have only U and D quarks in them. So this is what I mean by saying the UD sector. Okay, so I have used the SU true symmetry principles for symmetry between U and D quark, and we know that this is not an exact symmetry but an approximate one, since their masses are different by 2 to 3 MeVs. And so with this, what we aim to do today is to expand and talk about SU3 symmetry, where we will include the S quark in our discussion, and finally we will be able to talk about all the pseudoscalar mesons and baryonic octet and other cases as well. So so this is our title, symmetries and the quark model. This is basically second part. The first part, which I have not written here, is basically the hadrons in the UD sector. And today's talk, although you can also call it hadrons in the UDS sector, in a way you can also say that we are going to talk about symmetries and the quark model in the second lecture, where we are going to talk about the SU3 flavor symmetry. And as I have already talked about in my previous lecture as well, what we aim to do in this lecture is, with the help of the YI3 plots of the UDS quark and UDS antiquarks, we aim to construct the quark states of meson nonet, so that we can talk about both pseudoscalar and pseudo-vector mesons and finally obtain their flavor state functions. And the second aim is we will consider this 3-3-3 scenario and construct the baryonic quark states. Okay, so let's first talk about the SU3 group and briefly. Now again I have just written here for the sake of completeness. Well, it all started with the unitary group UN, which are basically the groups of n-dimensional unitary matrices. And then what's so special about it? Well, the SUN special, it's basically a subgroup of UN with the constraint that the determinant is equal to 1. Now the generators of UN are n-dimensional Hermitian matrices with a vanishing trace, and there are n square minus 1 such matrices. The rank of a group is the number of generators, which we know, which is written as a diagonal matrices. So the rank of SU2 is 1, rank of SU3 is 2. Now what's the simplest scenario here? The simplest case is the unitary group called abelian group U1. This group has its elements which are basically all complex numbers with the absolute value of +1. So we write it like this. Now the group SU2 is the group of unitary two-dimensional matrices with the constraint determinant U equal to 1. And as I have already discussed before, that this group describes the in particular the symmetry of isospin in nuclear and particle physics. So now each element of SU2 is a 2 by 2 unitary unimodular matrix and can be written using the alpha i's as 3 real parameters in this way. And if I talk about the generators of the Lie algebra for this group, if I name them I with index small I, then these are the generators, 3 generators, and I am writing them in terms of the Pauli matrices which satisfy the commutation relation here. Now with this discussion about U1 and SU2, we are able to talk about the SU3 group. The elements of SU3 group can be written down in this form here in terms of 8 3 by 3 traceless Hermitian matrices lambda k and 8 real parameters k. Now there exist 8 independent matrices of this type, and they are called the Gellmann matrices, lambda 1, lambda 2 up to lambda 8, where the matrices lambda 1, 2 and 3 are simply the 3 Pauli matrices bordered with row and columns of zeros here, you see. Okay, so the lambda matrices satisfy the following commutation and anti-commutation relation. These are the two very important relations, where the completely antisymmetric coefficients, which are the structure constants of the Lie algebra, and the completely symmetric ones, dijk, are given in this table. So both Fijk and Dijk, you can find it here. I've just written it for the sake of completeness. Now, similarly to the case of SU2, the generators of SU3 in the self-representation can be defined like this. Fi is half of lambda I, which satisfy the commutation relation Fi Fj I small Fijk Fk. Now out of the 8 generators Fi, only 2 are diagonals, F3 and F8, which corresponds to the fact that the algebra of SU3 has rank 2. The eigenvalues of I3, third component of isospin at hypercharge, can be written as this. Well, now we know that the SU2 flavor symmetry described previously is almost exact because of the difference in masses of the up and down quarks is small, and the Coulomb interaction represents a relatively small correction to the overall Hamiltonian compared to the small interaction. Now, what we are going to do is to include the strange quark in our discussion. Now, we know that the mass of the strange quark is somewhat greater than mass of both U and D quarks. So we don't have an exact symmetry. But again, this mass of S quark is not very much different from them, and so we can treat the strong interaction as if there is an approximate symmetry between the U, D and S states. So the assumed UDS flavor symmetry can be expressed as this in a matrix form. If you refer to my last lecture, you will find I have done the similar discussion there, and the 3 by 3 unitary matrices depend on 9 complex numbers, so 80 real parameters. But again, there are 9 constraints from this unitarity condition, and as a result we have got 18 minus 9 equal to 9 linearly independent matrices. These 9 matrices form a U3 group. Now, as before, a matrix is simply the identity multiplied by a complex phase, one matrix, and it is of no interest in the context of flavor symmetry. So we are left with the remaining 8 matrices which have determinant U equal to 1, and so form an SU3 group. The 8 matrices, which are the Hermitian generators, you can write it as T half of lambda. Sometimes I write F, but sometimes, most of the talk I will be talking with T here. And also this is the standard operator notation. In the SU3 flavor, so I can write the 3 quarks like this: U, D and S, 1 0 0 0 1 0 and 0 0 1, most simplest form assuming. And then in this SU3, the UDS flavor symmetry contains SU2 UD flavor symmetry, which allows us to write the first 3 matrices, lambda 1, lambda 2, lambda 3, like this. Okay, you see here. The third component of isospin is now written as this: UD equal to half of lambda 3 with this following property. Here, I3 counts the number of up quarks, number of minus the number of down quarks in a state. As before, we have defined the ladder operators T plus minus like this: half of lambda 1 plus minus I of lambda 2, and its operation is just like this. Fine. Now let us consider the matrices corresponding to symmetry between U and S quark and D and S quark. Here, U and S for lambda 4 5 and D and S lambda 6 7, along with these two. Here in addition, we have got lambda 3, which have got two other traceless diagonal matrices. However, the 3 diagonal matrices are not to be independent. So let us define an 8 matrix lambda 8 as the linear combination of this, okay, which specifies the vertical position in the 2D plane. So now previously we talked about only one dimensional plane before when we were talking about SU2 symmetry for UD quarks, and now here we have got 2-dimensional plane since we have included the S quark here, and as a result we will be working in this 2D plot. Now we only need 2 axes or 2 quantum numbers to specify a state in the 2D plane, I3 and Y. The other 6 matrices form 6 ladder operators which step between the states. Here, these are the definitions for T plus minus, V plus minus and U plus minus. They operate like this between the 3 states with the following definitions: I3 equal to half of lambda 3 and Y is 1 by root 3 of lambda 8, and the 8 Gellmann matrices. These are the ones. So for UD, lambda 1, lambda 2, lambda 3 is important, and US symmetry lambda 4, 5 along with lambda 8, and for DS symmetry lambda 6, 7 along with lambda 8 are important. Now, talking about quarks and antiquarks in the SU3 flavor in YI3 plot, you can represent it like them. Here I have just written down the I3 operation and its effect on U, D and S quarks, and also the antiquarks. Note that the antiquarks have opposite SU3 flavor quantum numbers. So another very interesting important thing to note is that the SU3 UDS flavor symmetry contains 3 SU2 symmetries, UD, US and DS. Now if we consider just the US symmetry, then this V is basically corresponds to the V spin which has the associated SU ladder operator. Fine. Similarly, we have got the U spin for DS symmetry, and I have already talked about the T spin for UD symmetry before. The effect of the 6 ladder operators are shown here. Note that all other combinations apart from the ones written here give 0, and this is the pictorial diagram. So before I move forward, let me just summarize or sort of point out the difference between SU2 and SU3 groups. So this is what we have done now, and remember, if you remember my last lecture, so this is what we did before. Since we were talking about UD, so it was a straight line, and these are the T operators which we have written down before, and this was the relation or result of operation of T operators, T ladder operators on U and D. And here, instead of just 2 T ladder operators, we have got 6 ladder operators. And the next difference was, if you can see, if you all remember that from 4 possible combinations of isospin doublets, we obtained a triplet of isospin 1 state here, 1, 2, 3, and 1 isospin singlet 0 state here. So we write it as 2 direct product 2 equal to 3 direct sum 1 here. In the case of SU3, this I will show today, we will write it as 3 cross 3 bar equal to 8 plus 1. Okay, so now with this technology we move forward to our first application, which is discussing about the light mesons consisting of UDS quarks. Fine. Now the first step which I'm going to talk about right now is the graphical construction of this meson nonet states. Fine. Now you see, remember the 3 direct product 3 representation, 3 direct product 3 bar representation. So that thing I have shown here in the diagram, UDS, U bar, S bar, T bar. Now how to proceed? So we start like this. So this is the UDS. Now in each vertex I am going to draw an triangle corresponding to an antiquark. So it is 3 cross 3 bar, and so for the sake of clarity I am just removing the nomenclatures of quarks, and so what we are going to talk about is this. So, and what do we get as a result is this. These are the 9 states which we get. Fine. These are the 9 states. 1, 2, 3, 4, 5, 6, 7, 8, 9. And you see, these are the states which I have noted it down here, and this is just simply so this represent the pseudoscalar meson. So the first step we have done it, which is the graphical construction of this meson nonets. Now the second step is the mathematical construction using the ladder operators. So what we did now, or what we have to do now, is to use the ladder operators to construct the UDS mesons from the 9 possible QQ bar states. So this is what we have obtained. Now it's important to note that the three central, the three central states, all of them have y is equal to 0 and I3 is equal to 0. And this can be obtained using the ladder operators and orthogonality. Now remember what we did for the case of SU2 symmetry between UDS quarks. We start with the outer states and then we can reach the center in 6 ways, like this here. So we have to use the corresponding ladder operators. So this is what you get as the result. Note that only 2 of these 6 states are linearly independent, but there are 3 states with y is equal to 0, I3 equal to 0. Therefore, one state is not part of the same multiplet. That is, it cannot be reached with ladder operators. So first, we form 2 linearly independent orthogonal states from this. Okay. Now, if the SU3 flavor symmetry were exact, the choice of states wouldn't matter. However, since the mass of S quark is greater than that of U or D and the symmetry is only approximate. Now, we observe 8 light mesons with mass of the order of, we observe 3 light mesons with mass of the order of 140 MeV. These are the ones, pi plus, pi 0 and pi minus. Now, we identify one state, the pi 0, with the isospin triplet, which we have discussed in my last lecture, this one. The second state can be obtained by taking the linear combination of the other 2 states, which is orthogonal to the pi 0 in this way. And with orthonormality, we get this psi 2. Note that the final state, which is not part of the same multiplet, can be obtained by requiring it to be orthogonal to both psi 1 and psi 2. And as a result, you get this singlet state. It's quite easy to check that psi 3 is a singlet state. Remember how you do that using the ladder operator? Because if it's a singlet state, then whatever operator you apply on it, the result will be 0, which indeed confirms that psi 3 is a flavorless singlet. Therefore, the combination of a quark and an antiquark yields 9 states, which break down into an octet and a singlet. So this is the octet and the flavorless singlet. And in the language of group theory, we write it like this. Fine. Okay. So now on to the next application, or the final application, which is combining the UDS quarks to form baryons. Okay. So, but we have already seen that constructing the baryon states is fairly tedious process when we derive the proton and delta plus and also the neutron wave functions. So for the time being, we will consider here only the first step, that is the graphical construction of the multiplet structure, rather than deriving all the wave functions. Fine. Okay. Now, whatever we are going to talk about here will also be relevant for the case of color quantum number, which I am going to talk about in my next lecture. Anyway, so regarding the UDS baryons first. So let's first combine the 2 quarks. Again, I am doing the diagrammatic approach and you get these states here. Note that this yields a symmetric sextet and an antisymmetric triplet. This thing here, symmetric sextet and an antisymmetric triplet, written like this. Okay, good. And now what do we do next? We add the third quark. So this is what we did before. Now we add the third quark to it, and so the result is this cross this, and so we have to do the sum of these two possibilities, 1 and 2. 1 and 2. So best considered in two parts, building on the sextet and triplet. Again, we concentrate on the multiplet structure for the wave functions. Yeah, I'm not going to talk about since I've already discussed before. The first part, let's talk about the building on the sextet, 3 cross 6 state, which yields 10 plus 8. You see, this is the way how it is done. You can do it by yourself and check in your copy, and I've just written one of the states. Okay, so this is the symmetric decuplet and this is the mixed symmetry octet. The next one is building on the triplet, and this is just similar to what we have done before, right? And we get this mixed symmetry octet and totally antisymmetric singlet. Now you can verify that this wave function is indeed a singlet by using the ladder operators. You just apply it as t plus here, and you see the result is 0. So this is what we have done and what we have obtained. Again, I'm not going to talk about the wave function part here. So just the first part, the multiplet structure, qualitative understanding through geometrical approach. And in summary, the combination of the three UDS quarks decomposes to this pattern, 10 plus 8 plus 8 plus 1. Okay, and this is what we experimentally observe. This thing, see, the symmetric decuplet. Remember, I talked about it in my first lecture, and regarding this is the, yeah, okay, two baryon decuplet and baryon octet cases. So we are good, and now just a glimpse of this entire lecture while talking in the classroom. Anyway, and these are my students of the previous batch, and this is our lab. Basically, I was taking this class in our lab here, and you can see again the same structure which I'm talking about. Okay, so what did we learn here in today's lecture? What we learned is basically that the SU3 flavor is a group of approximate symmetry for strong interactions, and it appears that all mesons with spin parity, this I've just talked about few only, can be arranged in octets and singlets, and all baryons into singlets, octets and decuplets.